Hello again. This is Math 2232 coming to you from the College of DuPage. And this lecture is the conclusion of a lecture about polar coordinates, their graphs, their equations, and such. As always, be attentive while watching this video. Let's identify a few of the more common graphs as they appear in polar coordinates so you can look at them and recognize them. All right, so lines. Now, lines have simple polar coordinate equations. And the equation for a line that goes through the origin is going to be theta equal beta. That is, theta is a constant. We can see this is a line by converting it to Cartesian coordinates as follows. We know if theta equal beta, then theta is equal to the inverse tangent or arctangent of y over x, equaling beta, and that means that y over x is equal to the tangent of beta. So I multiply both sides by x, and I get that y is equal to tangent of beta, which is a constant times x. So this is a line that goes through the origin and makes an angle of beta with a positive x-axis. Or in other words, is a line through the origin with a slope of tangent of beta. This could be a positive or negative slope depending on what beta is. If we consider a different line that doesn't go through the origin, and it's not the only line that doesn't go through the origin, but it is a line that doesn't go through the origin, we can say that r cosine theta is equal to a constant. Well, you see, this really is x, so this says this is x is equal to a constant. That means it's a vertical line, x equal a. Similarly, this is y equal b, so this is a horizontal line. To make these your own, I'm going to ask you to do a problem here. I encourage you to try this. Graph theta equal 3 pi over 4, r cosine theta equal 4, and r sine theta equal minus 3 on the same axis, on the same xy axis. You know what to do. Let's see how you did. And if you got it done, congratulations. If not, you'll learn something. So either way, you win. All right, we start with the positive x-axis and we go over to 3/4 of pi. So we are here, and that's what we get. So that angle is always 3/4 of pi, and so that's going to be all of those. This is x equal 4. That's a vertical line going through there. And this is y equal minus 3. That's a horizontal line going through there. All right, let's look at some other equations. Suppose we just say r is equal to a constant. Well, this equation is saying that no matter what angle we've got, the distance from the origin must be a. So if you think about it for a while, that means this is exactly the definition of a circle of radius a centered at the origin. So this is a circle of radius a centered at the origin, and it's also one of the reasons we might want to work with polar coordinates. The equation of a circle centered at the origin is a much nicer equation in polar coordinates than it is in the corresponding Cartesian coordinates. In Cartesian coordinates, of course, it would be x squared plus a squared equals, or excuse me, x squared plus y squared equals a squared. Here's another one. Suppose we have r is equal to 2a cosine theta. Now, we did look at a specific example of this in when we were converting equations in a previous example in the last lecture. This is a circle of radius, the absolute value of a, and I'm saying the absolute value because a could be negative, and it has center at a comma 0. And a might be negative, and in fact it was in our example before, so that's why we need the absolute value. And so this ends up being centered on the x-axis. And if we say r equal 2b sine theta, this is similar to the previous one, is a circle of radius absolute value b, but its center is at 0b. So this is centered on the y-axis. This one's centered on the x-axis. And if we have this one, and you might have to think about this for a while, but this is a combination of 2a cosine theta and 2b sine theta. So this is a combination, and this, if you complete the square twice, you can show, that's actually a good exercise for you to try to do, that this is a circle of radius, the square root of a squared plus b squared, and center AB. In other words, this is the general equation of a circle that isn't centered at the origin. Let's check to see your understanding by doing a problem. Asking you to graph r equals 7, r is equal to 4 cosine theta, and r is equal to minus 7 sine theta on the same axis. You know what to do. Now, if you were successful in doing that, congratulations, good job. If you were not successful, you have an opportunity to learn something. Let's see how you did. So r equals 7 is going to be centered at 0, 0, radius 7, so that's the big red circle. R equal 4 cosine theta is going to be centered at 2. Remember, there was a 2a there. It's centered on the x-axis, so that will be the blue circle. And r equal minus 7 sine theta is going to be the green circle. It is centered at minus 3 halves, or 7 over 2. 0 minus 7 over 2, and it's of radius 7 over 2 as well. So both the blue and the green are tangent to the origin, and that's what we ended up with. Now note it takes the range of 0 to 2 pi for a complete graph of r equal a, and it only takes a range of 0 to pi to graph the other circles given here. And you can verify that if you want with the correct table of values. We're going to talk briefly, and there will be problems that will come up dealing with other shapes, and we'll talk briefly about them. There is a shape called a cardioid. A cardioid is a heart-shaped figure, and it's a curve who is defined as the locus of points lying on the circumference of a circle that is rolled externally without slip on the boundary of another circle of the same radius. Here's what that means. You've got a circle of a given radius. You got another circle that you're going to roll around it, and we're graphing what happens to the point on the radius of this second circle as it rolls around the radius of the other circle. So this point, as this circle here rolls around this one, will trace out the cardioid. And it's cardioid because it looks kind of like a heart-shaped thing. There are polar equations of cardioids. Here is one, and you have r and theta, of course, which have a, and that has to do with the dimensions of these circles. For the same a, if we put that into Cartesian form, we would get a very much more complicated thing. So you see, polar equations do help you if you're dealing with a cardioid. And you see, again, the parametric equations are very different than either one of those. So again, these are three things that are related, but three things that are different one from another. There are also things called limacons, and I think technically the C is supposed to have a little exit mark under it, but I didn't invest a lot of time trying to find that. Now, a limacon is different from a cardioid, and it is similar, but you take two circles, a blue one and in this case a black one. You're going to be rolling the black one along, but instead of taking a point that's on the circumference of the black circle and following it, you take any point inside the circle and you roll it around. So you see this ends up being a different path, a different definition. And here are some polar equations for those. So here we have r is equal to 1.5 plus cosine of theta. And we get something that looks like that. Here we take r is equal to 1 plus cosine theta, and you get something that really is pretty much of a cardioid. But then here, if we take r is equal to 0.5 plus cosine theta, what happens is it has a loop. So it loops around itself and goes over. So again, limacons will come up from time to time. Now, I talked about cardioids and limacons, but these can be broken up into a few cases. So cardioids will either look like r equal a plus or minus a cosine theta, or r equal to a plus or minus sine theta. So they have a graph that is vaguely heart-shaped, and they will always contain the origin. Limacons with an inner loop, and I showed you one with an inner loop, are the form r is equal to a plus or minus b cosine theta. These numbers are not necessarily equal. Or r equal a plus or minus b sine theta, with a less than b. So if a is less than b, there will be an inner loop. And these will always contain the origin. But you can have limacons without an inner loop, and that's if you have a plus or minus b cosine theta, or r equal a plus or minus sine theta, but this time a is bigger than b. These won't have an inner loop and do not contain the origin. And finally, you have a figure that looks like an 8 or perhaps an infinity symbol called a lemniscate. And these have been studied by many people, including Bernoulli. They're polar equations. If you look, you notice that there's symmetry here. So these end up being r squared equals a squared cosine of 2 theta, and the 2 gives you the 2 pieces. And so, and if you turn that into Cartesian coordinates, of course, you would get this. You might have to work a little bit to actually get this x squared minus y squared, but it actually comes from a trig identity. That actually would be a good problem for you to work on. Okay, so here are some for you to graph. So why don't you try graphing r equals 5 minus 5 sine theta, r equal 7 minus 6 cosine theta, and r equal 2 plus 4 cosine theta. And again, you can certainly look at your notes, but this gives you some experience. You can pick some points and so on and so forth. You know what to do. Let's see how you did. If you got these, congratulations. If not, focus on what we cover and you'll learn something. We'll see how you did. Now here we were just picking values for theta and graphing these, and you see that I do have a xy like coordinate system that is here. So here you see that since I get a cardioid opening this way, and here's the points that I picked, and I plugged them in to get that. So this was the 5 minus 5 sine theta. I plugged the values in, and I got that. Here, when I plug the values in, I get a cardioid, but notice that the orientation is different. Now again, here the two were equal. This is a cardioid. Here this is really a limacon, but it's very close to being a cardioid, and it is kind of heart-shaped. And down here, you can see that the 2 is less than the 4, so I do get an inner loop for that. And later on we'll find areas inside these and tangents and so on and so forth. We'll be doing calculus on such figures. One final thing that I should mention, in the third graph that had an inner loop, sometimes we need to find the value of theta for which the graph will pass through the origin. So in that case we were saying 0, which is the origin, is equal to 2 plus cosine 4 theta. So we will subtract the 2 from both sides, divide by the 4. We have cosine of theta is equal to minus 1/2, and that means that happens twice, from 0 to 2 pi. It happens at 2 pi over 3 and 4 pi over 3. And you might say, well, why would I want to do that? Well, we're going to need to do that to find limits on integrals. So this is a good skill to keep in mind. There are other kinds of graphs, and just for exposure to this a little bit, I'm going to ask you to try to sketch the graph of r equal to cosine 3 theta. Now you might be looking at this as, yeah, haven't we done this? This is a circle. No, the circle that we had didn't have 3 theta. The circle we had was only theta. And so you want to find out what happens here. You know what to do. Let's see how you did. Okay, here's some values that you could pick, and in fact, I do something that maybe is useful, because you might say, well, gee, I can find out what r is for theta, but this is going to be awkward to graph. Is it possible for me to graph these in a way where I don't have to worry about r so much? And it is, because you see, I say r is equal to 2 cosine 3 theta, but in this case, we're going to write the polar equation in a parametric form. We haven't done that yet. So we got x is equal to r cosine theta, but r was up here. Now this is, so x is going to be 2 cosine 3 theta times cosine theta. If you think about that, this is what I referred to earlier, where we say sometimes r is equal to r of theta. And so this is what we get for that. Y is always going to be r sine theta, and so we plug it in. We can pick a bunch of values for theta, either getting r or just finding x and y with this. But what you're going to find out is that you start here, you go down, and then you loop back. Then you loop up here, getting that, then you come back and you loop back, and so on and so forth. You might say, oh, I got a, and this is called a rose, I got a 3-petaled rose because theta, because the argument of the cosine was 3 theta, and that answer is correct. And so what you will get is a rose with petals, with a petal along the x-axis for that, and you will get in petals. If you do a sine, you won't get this on the axis. You'll get that one of the petals is on the y-axis. Okay, to summarize a bunch of these things, then we have circles and lemniscates that are summarized here, and you see here your lemniscate is slanted because you have the sine of 2 theta. Here was the one that was similar to Bernoulli's, that is a cosine of 2 theta. Those are lemniscates. These are the circles that we talked about before. These are some rose curves, and these are some limacons with what I said, summarized before. So this isn't a bad chart to think through and things like that, because these polar graphs can be very useful, and in fact can be very pretty. I guess beauty is in the eyes of the beholder, but this is a graph that we have r is equal to cosine of 2/3. Now this isn't an integer, and you said, oh, I thought we would get a rose. Well, you don't actually get a rose, because you only get a rose when this is an integer, cosine in x or sine in x. Whenever you get a non-integer, you get something wilder and crazier, and you get figures that look like this. And here's a nice research article, if you want to glance about that, about these things. And this was generated by some software called Maple, which is a CAS system. Anyway, soon we're going to be doing calculus on these curves, but this is to provide you with the background so that you can understand the calculus. And now the calculus is the same, but this particular is much more graphing technology than we're going to be using this summer at COVID COD. So calculus on this soon. In closing, now more than ever, time is precious. Each day must count. Do the math that will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. God bless you all.